Assalamualaikum and good morning everybody. So today we are going to continue what we have left off last week, which is we have learned on how induced voltage are developed in a simple single loop rotor inside a permanent magnet stator, in which we have calculated that the induced voltage is equals to some kind of constant multiplied with the total flux inside the machine as well as the speed of the rotor. So now we will look at how we can determine that from a real DC machines, because we know that the real DC machines doesn't just have a single loop that are not wrapping around anything, but we have actually multiple loops that are wrapped around a ferromagnetic core. Okay, sorry. Okay, so first of all, we need to go through what we call a roto construction. So we know that the roto is comprises of a laminated sheets of ferromagnetic material, in which they are built in layers by layers to perform a block, and then you have some kind of wires, or not wires, coils that are wrapped around that core. Okay, so to know how many conductors, because for a single coil we know that there are two conductors, right? The side, remember with the single coil we have A, B, C, D, and there are only two conductors here that are contributing to the induced voltage that we have from the machine. Okay, so so basically with this single coil we got the machine constant, or the K we will call later on as 2 over pi, if you can still remember from the equation. So the number of conductors on a rotor when there are multiple coils and multiple turns. Okay, so coil is something like this. Okay, this is like one coil, and there are actually multiple number of turns per coil. So basically you wrap 1, 2, 3 and so on, hundreds of them typically on each coil. So the number of conductors on rotor will depend on this, on how many turns as well as the number of coils on rotor. So the number of conductors is basically 2 times number of coils and number of turns per rotor, because we have two conductors that are contributing to the induced voltage. Okay, the second one is the term electrical angle and mechanical angle in degrees. Okay, so electrical angle means the waveform, or in this case the AC waveform that are created inside the machine, because we have actually AC voltages inside the DC machines, and we got DC because we have commutators, right? So inside of that is a alternating current. Okay, so basically the electrical angle means this angle. Okay, the waveform angle, and the mechanical angle means the rotation around the loop. So the rotor, so say that this is arbitrarily 0 degrees. So as the motor rotates, okay, say it rotates here, we know that it rotates to 90 degrees mechanical angle. So that's the difference. So the electrical angle, or how many degrees that we have at the waveform, will depend on the number of poles. So we know that if we have like permanent magnet north and south, we have 2 poles, right? So if we have just 2 poles like this, or one pair of pole or 2 poles, simply the electrical angle will be equal to mechanical angle. So whatever waveform that you see here, so for example 180 here, so the rotation at the mechanically also 180. So you have multiple poles, so if you have, for example, 2 pair of poles, so that means you have 4 poles, then the electrical angle is 2 times the mechanical angle. So if electrical angle are 180, then mechanical angle already gone through 360. Okay. Now, we have seen from the previous class that in one of the videos that the conductor or the coils are connected to a commutator, depending on, well, for example, if you have three commutators, then you can connect one side of the coil at one commutator and the other side at the next commutator. Okay, but basically in machine design or the electrical machine design, you have two types of winding and how you can connect that to the commutator. Okay, so you have what we call a lap winding, and we can see that coil 1, for example, are connected to commutator number 1. One end of it is connected to commutator number 1, and the other end, the dot here means they are at the back, okay, of the rotor. Okay, so it will go and connect to the second commutator. Okay, so the next coil will connect from 2 to 3. Okay, so at any so basically, if we are connected, if the brushes brush through this commutator, then the current will flow through coil 1. Okay, for wave winding, basically the differences are on the set of commutator ends that are connected to the coils. Okay, so you can see that instead of, like, for example, in lap winding, coil 1 and coil 2 kind of like share the same pole. Okay, but and the in wave winding, you have end of coil 1 with north and south poles there, and then end of coil 2 have also its own north and south pole. Okay, so in lap winding, you basically the front of the wind, or not the front, the one end of the all the coils share the same magnetism poles. Okay, and the other end of the coil share another pole. Okay, so but with wave winding, it's different, right? So in this case, the coil, the first coil and the second coil have kind of like a what we call connection that are not next to each other. Okay, so in lap winding, you can see that the connection is one end is at one commutator and the other end is next to it. But with wave winding, you have the connection here, and then it will take so far to go to the next connection, and it is more evident inside this diagram lah. Okay, so you can see also that in here, this is the south and this is the north, and you can see that with wave winding, you have north, south, and north again, and south again. So it is a little bit different from the construction of a lap winding. We also have a coil that we call a frog leg winding. So you have a wave windings connected with a lap winding. Okay, so it's a combination of that too.